Okay, so chapter 9 is about work and kinetic energy. So one thing that I want to point out here in this chapter is that all forms of energy are scalar quantities, and that is fantastic news because that means it does not matter the direction. We do not have to find vector components. There's not going to be any force diagrams. Oh, it's going to be so much fun. All right, so we're going to be learning how to solve some of the same problems that we've solved before, but this time we're going to be using energy methods. So when we do get to our exam, we will need to be careful that we are solving using energy methods and not using kinematic methods or even force methods, not applying Newton's second law to doing these problems. So I'm going to be testing you on the method, not just can you solve the problem, but can you do it in this way by using energy conservation methods. All right, so let's talk briefly. Kinetic energy has to do with, it's the energy related to motion. And you'll notice that the kinetic energy is 1/2 the mass times the velocity squared. Really, we would rather say speed there because we have a scalar quantity. And you might say, well, what about the velocity? Regardless of the sign, positive or negative, the velocity gets squared. So those vectors being multiplied together gives you a scalar quantity, actually. So it all turns out. Now, let's talk about work. I'd like to focus on that a little bit because that's one of the things that it's another word that is commonly used in English that has a completely different meaning in physics. So work in physics has to do with a force being applied and some kind of displacement being covered. And the general form, if we look at just in one dimension, the S means one dimension. The S is just their generic displacement, whether it's X, Y, or Z. And this F sub S means that we're just looking at the component of the force that is in the same direction as the displacement. That is really critical. We're going to be looking at any angles that might be between F and the force and the displacement. Now, if we have a constant force, we would not have to integrate. So if we had a constant force, we would take the force outside of the integral. We would just integrate ds from S1 to S2, and we would just get F times a delta S. And again, this is for one-dimensional motion. Now, if we are going to 3 dimensions, which is where we are going to generally be treating our problems, even if they're not fully 3-dimensional, we can still use this dot product. And I do want to take some time to talk about the dot product and how we do this calculation. So the expression itself, notice the dot product is not multiplication. It is a vector multiplication process. And we're now going to be using R as our generic displacement. R is, in general, can be written as, an X component in the I hat direction, some Y component in the J hat direction, and a Z component in the K hat direction, just like we talked about before. Okay, so if we have a constant force, then we do not have to integrate the force, and then we just get F dot dr. All right, well, that's going to make more sense when we look at this dot product a little more. So I'm going to show you kind of what the dot product means and how do we deal with it. Okay, so first of all, the thing with the dot product is that it seeks out a parallel component of one vector compared to another vector. So far what we've been doing in this course is any kind of components that we find of vectors are always going to be, or they had always been either the X component or the Y component, maybe a Z component. I don't know that we've done any of those, but we were looking at components along our set axes. But the dot product is more powerful and more convenient because it seeks out a parallel component of one vector in the same direction as another vector, not another axis of the coordinate system. Okay, this will become clear as we move forward. So for now, let me just show you how to operate this. Okay, so anytime you have the dot product, this dot product can be written as magnitude of the magnitude of the vector A, magnitude times magnitude of the vector B, times cosine phi. And this cosine phi, this phi is the angle between vectors A and B. It's not an angle that's necessarily given in a drawing or in any kind of diagram, but it would be an angle not with an axis, but with, from one vector to the other. So if, for example, I had these random two vectors A and B like this, and I had this angle between them, this is showing you what, how angle phi relates to these vectors. But one thing that, just to kind of give you a sense of what's going on here, what we can do is say, all right, well, vector B, what if I wanted to know the component of vector B that was lined up in the direction of vector A? Then I could say, well, here, this vector right here, I could call this vector B times the cosine of phi, right? Because it's the component of the B vector that's lining up in this direction, and I would call that part of it B cosine phi. Well, if I now take this B cosine phi, it's now lined up with vector A. So this is showing you that this B cosine phi part of it is really just showing you, this is just the parallel component of B that's parallel to vector A. If we do that now, instead of generic A vector and B vector, let's now look at it in terms of this, the work. So work being the integral of f dot dr, that means that we're going to be looking at, the dot product itself would seek out what part of this force F is in the same direction as dr. That's what it means. So instead of A dot B, I have F dot dr. There's still two vectors, and I'm looking at finding that parallel component, and that's why the cosine enters into this expression. So let's look at some issues with work. So anytime you have work done, when work is done on a system, okay, a system, this is just a collection of objects that we're talking about. The system can be one object. Okay, so you can have a system that is just one object. It can be two objects or more. But anytime work is done on the system, the energy of that system is going to change. So that work could be positive, that work could be negative. If energy goes into the system, okay, so positive work means energy enters the system, whereas negative work means that energy exits the system. Okay, so at first glance you might say, wait a minute, you said that all forms of energy are scalar quantities, and work is a form of energy, so therefore work should be scalar. Yes, it is, but this positive and negative does not indicate direction. It does not mean left or right or up or down, but it rather refers to whether energy is going in or energy is going out. It's not a vector. So just like your bank account, you have if you look at the transactions in your bank account, you will have positive ones, you will have negative ones. The positive ones, it doesn't mean that you had money moving to the right or moving up. It just means that money went in. And negative doesn't mean it went left or down. It means that money left the system. So that's exactly what it means here. So even though work could be positive or negative, it still is a scalar quantity. It is not a vector. Okay, so this delta E of the system, so if there's a change in total energy of the system, that means that there was work done by external forces. Okay, so work done by external forces to the system. Internal forces do not do work. We'll pick that up a little bit later. Okay, so another consequence of this is the work kinetic energy theorem. So if work changes the amount of energy in the system, either increasing it or decreasing it, then that means that when work is done, there's going to be a change in the kinetic energy. Well, a change in kinetic energy just means it's the final minus the initial kinetic energies. And that means that we have 1/2 mv final squared minus 1/2 mv naught squared. Okay? And notice that the sign, positive or negative, of the work will also show you which way the energy goes. So here, if your kinetic energy is, okay, so let's say that you started with no kinetic energy and you ended up with a large amount of kinetic energy. So if this first term is large and your initial velocity is, let's say it's 0, you can see that the work is going to be positive. So your energy increased. But what if you were slowing down? What if your final velocity is less than your initial velocity? Well, in that case, you're going to get a negative value for work, and that will indicate that you slowed down, energy was lost from the system.